Hello students, welcome to the EN 401 lecture on littoral processes and sediment transport. Here's our roadmap for this lecture. We're going to talk about cross-shore transport, and then longshore transport, and then move on to the equilibrium beach profile. So a big question before we head off into this lecture is, are all beaches created equally? Now if we take a look at the two photos below, both are beaches, right? But both are very dissimilar from each other. The only similarity being that there's land and water. So we can see some pretty obvious differences between the two beaches. On the left, this nice beach you might see in Pensacola when you're at flight school has lots of nice fine sand. And this beach on the right has a lot of large gravel particles that make it up. So we can see that not all beaches are made from the same exact type of sediment. Another thing that we see is this beach on the right here has a pretty steep slope, right? It's a pretty steep slope on the beach on the right. And on the left, our beach is relatively flat, right? So we can see that there might be a correlation between the size of the sediment at the beach and the slope at the beach. So we'll take a look at that in this lecture. And then also, what are some other factors that might impact how a beach is formed? Right? Do all beaches abut the same body of water? Are they all subjected to the same types of waves or winds? So there's a lot of different things that might impact how a beach is formed. So per the roadmap, we're going to start talking about cross-shore transport, right? And start this off, we've got a picture here depicting the profile of a beach in summer versus winter, right? And we see that our dunes and both are at about the same elevation, but once we move to the right of the dunes, things get a little bit different. So in the summer, we've got lots of sand here in the berm between the dune and the high water mark. In the winter, this whole berm is now gone, right? So it's basically the dune, and we go, right down into the high water mark. So this is pretty typical, seasonal beach profile. And the question is, why are there differences in the beach profiles? Well, the simple answer is the waves are different in winter and summer. So typically in the winter, beaches see larger waves, and so these larger waves erode the beach. They erode the berm, and in the summer we see smaller waves, and those smaller waves allow for the berm to be built back up. So the constant erosion and accretion of sand from the beach profile is called cross-shore transport. Right, so cross-shore transport has to do with the movement of sediment that is perpendicular to the beach face. So if this is our beach face, that means we're talking about sediment that is moving perpendicular to the beach face. So onshore and offshore. So away from the beach or onto the beach. So we call onshore transport, we call that accretion. So if we're moving sand or sediment onto the beach, we call that accretion or deposition. And if sand is moving off, then we call that erosion, right? So accretion will build up the beach face and the berms, and erosion will pull that sand away, and we might see some sand dunes building offshore. Or we sometimes call them sandbars. So sediment plays a big role in cross-shore transport. So we saw from the one of the early slides in this lecture that the size of the sediment particles at the beach can change how the beach looks or how it reacts. And Same thing is true with cross-shore transport. The size of the sediment uh, will help determine if the sediment is going to accrete at a beach or erode from a beach. So if we have small sediments here, right, when a wave hits the beach, the wave will pick those sediments up and they'll stay suspended. And the longer they're suspended, the more susceptible they are to washing away. And if we went way far on the other end of the spectrum and had a beach that was just all boulders, if the boulders even got picked up by the water, they would fall very quickly. And so you're more likely to see accretion at beaches with larger sediments. So if we even think back to that picture in the early slides, the beach with the large sediments was steep, which means it had a lot of accretion, right? So we had a lot of these types of particles, and that picture on the early slide, and we saw that we had a steep beach, so that indicated we probably had accretion at that beach. So the other piece that affects cross-shore transport is wave period, right? So longer wave periods, right? So more time between waves means that there's more time for the sediment to fall back down into place, right? So a wave hits, the sediment gets suspended in the water, but if a new wave doesn't show up for quite some time, then that sediment has time to fall back down and not necessarily erode away and stay suspended. Okay, so shorter wave periods, right? So if wave comes one after the other, back to back to back, right? All that sediment that's been suspended never gets a chance to fall down, and that means it's more likely to be eroded away. And so this is a great picture here of sediment being suspended in a wave, right? We get this great plunging wave here, and a bunch of sediment is suspended as this wave goes through, right? And if another wave was right behind it, it would keep that sediment suspended and not let it fall back down. So we probably see a lot of erosion at that type of beach. All right, so how do we figure out if a beach is going to erode or accrete? Well, what we're going to do is we're going to calculate the fall time parameter, also known as FTP. And the fall time parameter is equal to H naught, which is the deep water wave height, divided by VFT. So VF is the fall velocity, which we'll pull off a chart that we'll see on the next slide. And T here is the wave period, so time between waves. So remember, H naught is deep water wave height, right? So deep water wave height divided by VFT. So if we get a large value for a fall time parameter, that means we have a high energy beach, so large waves or short periods, and we would most likely see erosion at that beach. Right, the smaller the fall time parameter, the less energy that the beach is seeing, and therefore we would expect to see accretion. So our fall velocity is related to our sediment size, and we'll see a chart on the next slide that shows how we can calculate those. But it should make sense that a larger grain size for a sediment is going to reduce the fall time parameter, right? So the bigger the sediment, the more likely we'll see accretion, right? And just think back to that early slide with those two different beaches. The sandy beach was flat, right? So that means it's probably dealing with a lot of erosion. Whereas that rockier beach was really steep, so it's getting a lot of accretion, right? So larger sand grain sizes will reduce the fall time parameter. And so how do we figure out if it's erosion or accretion? Well, we'll just compare the fall time parameter to 2.5, right? So if you calculate a fall time parameter that is greater than 2.5, that means we will probably have erosion. And if our fall time parameter is less than 2.5, that would indicate it's a low energy beach and we should probably see accretion. All right, so key in calculating the fall time parameter is finding the fall velocity. So we're going to use this chart here to find the fall velocity. Of note, the fall velocity on this chart is in centimeters per second. So that might cause some challenges when you're doing your calculation because we need units to cancel. And so if VF is in centimeters per second, you'll probably want to convert H naught to centimeters. That way your units all cancel out. All right, so the way we use this chart is pretty simple. You'll be given the grain size diameter of the beach. So let's just say our grain size diameter is 0.4 millimeters, right? And so this says in millimeters, our grain size diameter. So you'll be given the grain size diameter of the beach, and then you'll be given the temperature of the water. So these purple lines here, these are all temperature lines. So these all indicate temperature of the water. And if we look over here, we can see a 40, a 30, 20, 10, and 0, right? So each of these lines is labeled for their temperature. So if let's say we wanted to find the fall velocity of a sand grain that's 0.4 millimeters, and the water temperature is, it's pretty cold. Let's just say it's 0 degrees Celsius. We'll just follow this 0.4 line over until we hit our 0 degrees Celsius line, and then we'll drop straight down, and we'll see that our fall velocity is around 4 centimeters per second. So my line's not that straight because I freehanded it, but that means our fall velocity is about 4 centimeters per second. So we would then just plug this 4 centimeters per second into our VF and just make sure that our units are similar for our calculation. And then once we calculate the fall time parameter, we can compare that to 2.5 to see if we're going to get erosion or accretion. All right, so what happens in the case of a large storm, right? So large storms, they bring what's typically called storm surge. So we think we've talked about this before, where the storm essentially is a vacuum and it pulls sea levels up. So so we get higher sea levels, and then the heavy winds of the storm cause large waves. And so the combination of those is really going to raise our fall time parameter. And we could see some extensive damage and erosion to our beach profile because of storm surge. So we've got a cross-section of a beach here, and we can see that we have some storm surge, and it's eroded all of this material and deposited it all out here. So our beach is much less protected now because we've even started to erode the dunes. And now whatever is built, maybe we have, some kind of building over here. Now that building is much more exposed to the beach or the ocean than it was before the storm. So that's exactly what happened at Camp Lejeune when Hurricane Florence came through in 2018. So on the left here, we have a picture of March 18th, 2018. So here's I'll just kind of draw a line that shows our dunes right here. And we can see that there's some solid dunes between, this building with the arrow and the water, which is sort of delineated by these three lines here. So we got some solid dunes here. So the Hurricane Florence came through, and then this photo on the right was taken on September 17th, so after the hurricane. And now we can see that those dunes have been here sliced in half. They're almost non-existent through here, and then they sort of come back out. So a massive amount of erosion. Those dunes used to be probably out to about here. So several feet of dunes has been eroded away, and now this building is much closer to the ocean than it was before. So this is a very dangerous situation if you work in that building, and that's something you probably want to get mitigated as soon as possible. So we've talked a lot about cross-shore transport, which is the movement of sand perpendicular to the beach face, and so now we're going to move on to long-shore transport. So I highly recommend watching this video, River of Sand here. There are several questions on the homework based on the River of Sand video. It really goes into depth on both cross-shore and long-shore transport and how those mechanisms work. But we'll talk about it briefly on this slide. So one thing we find is that waves always approach the beach at some angle, right? So here's our wave angle here. So we call this wave angle alpha. All right, so that's our wave approach angle alpha. So the waves always approach at an angle, and what happens is when the wave hits the beach, we'll just look at this point here. It'll pick up the sand and move the sand up the beach in the same direction that the wave is approaching. And that sand particle will stop when the wave stops going up the beach. So once it hits its maximum wave run up, and then gravity pulls that particle back down, and then another wave hits and pushes that particle up and then back down. So over time, you get sand flowing like a river of sand down the beach, right? So we call that longshore transport of sand. So remember, cross shore is perpendicular, so that's sand moving in that direction, and longshore is parallel, so sand moving in that direction. So both of those are occurring at the same time on any beach on any given day. So here's another depiction of longshore transport. Go ahead and click this link here, and you can watch that animation. It really shows how sand particles move because of longshore transport. So there's a couple different ways that the sand is moved in longshore transport. Here they are right here. You can go ahead and read those descriptions. But I want to talk about the two big factors that affect longshore transport rates and how much sand is being moved. One, I think is pretty intuitive, is the wave height, right? Big waves move more sand. I think that's pretty easy to comprehend. And then the second one is the average angle of approach that the waves hit any particular beach, right? So that angle alpha. So if the waves are coming in pretty much perpendicular to the beach, so a very small alpha angle, then you wouldn't expect to see a lot of longshore transport. But the greater the angle alpha, the more the sand is going to move parallel to the beach face, right? So the more longshore transport that we're going to see. All right, so all these dynamics we've talked about with cross-shore and longshore transport, they can all sort of be summarized in this equilibrium beach profile, which allows us to figure out some generic properties of a beach based on, essentially just the grain size diameter of the beach, right? So this was developed in 1977 by Professor Dean. That's an interesting name if you ask me. University of Florida. So he says that pretty much all beach profiles exhibit a common set of features, one of which is a concave upward shape. And he also found that fine sand beaches are much flatter overall. And so he developed this equation where we can determine the depth at a distance offshore solely based on the grain size diameter of whatever's at that beach. So we get this picture here. So this picture here shows a concave beach. And here is our equation that we'll use. D equals ax to the 2/3. So our depth is equal to a value a, which we'll determine on the next slide, times the distance offshore raised to the 2/3 power, right? So if we know the distance offshore and the grain size diameter, then we can calculate the depth. So again, here's that equilibrium beach profile equation here. So make sure you understand this and know how to use it. So the one thing we haven't covered so far is this A value. So A is a correlation to the average grain size diameter. And so we use this table here on the right to find our A values. Right, so if we have our grain size diameters given to us in millimeters, we can use this table to figure out what our A value is, and then plug that A value into our equation so we can either find depth or distance offshore given one or the other. So one thing to note is the A values are all given in meters to the 1/3, right? So if we're working in U.S. Customary units, we'll have to convert that, and the way we convert that is by multiplying our A value by 1.49. So just keep that in mind. All right, so how do you read this chart? So you'll be given a grain size diameter in millimeters, right? So on the left here is our tenths place, right? And then on the top is the hundredth place of our grain size diameter. So if we had a grain size diameter of, let's say, 0.65 millimeters, we'll go on the left here, we'll go to 0.6. That's our tenths place. And then we'll just go over until we find the 0.05, right? And where those meet up, that is our A value. So 0.65, A value is 0.179 meters to the 1/3. So we can use that to either find depth or distance offshore, given one or the other. So key point is larger grain size correlates to a larger A value, right? So if we go to our largest grain size of 1.09 millimeters, so our biggest grain size has the highest A value, and our smallest grain size, 0.1, has the smallest A value. So that means we'll see steeper beaches with higher A values, right? If A is larger, then D is larger given the same X. So that means we have a steeper beach with large sand grains versus a flatter beach with small sand grains. And that's what we saw on that early slide, right? We saw that sandy beach was nice and flat, and that super rocky beach was very steep. So this correlates nicely with what we have seen in real life. So go ahead and take a minute to open this up, and you can edit the A value in cell B2, and it gives you a graph of the beach profile, and you can see that the larger the A value you plug in, the steeper that the beach is. All right, so here's example 1. Be sure to attempt this problem and check out the example problem video. Here is example problem number 2. Again, be sure to attempt this problem and then check out the example problem video. A third example for the equilibrium beach profile, and a fourth example for equilibrium beach profile. And note that we're using the U.S. customary system of units, and remember that A value chart is all in meters, so make sure you do the conversion. All right, and here's our closing and review. So I hope you enjoyed the lecture. Thanks for watching.